Okay, so our next speaker is Sujith, and he will talk about a very well-known paper, and perhaps will take us a few presentations to actually understand everything about attention and stuff. But at least this would be a good introduction to the subject. So go ahead, Sujith.
Yeah, so greetings everyone. My name is Sujith Mandala, as Sir has already mentioned, and I'm here today to present the paper titled Attention is All You Need by A.Vaswani and his co-authors. So I have chosen this paper because it contains a powerful model known as the transformer, which has had a significant impact on current natural language processing tasks. So to begin my presentation, I will provide an outline of the paper. So this will include an introduction to the paper, a background research, the description of the proposed architecture, its training, the results, and the author's conclusion. Finally, I will provide a summary of the paper. Then getting into the introduction part, the authors introduce the problem of machine translation and state that the current state-of-the-art models for this task rely on a combination of recurrent and convolutional neural networks. So the authors aim to simplify the architecture for machine translation by relying solely on self-attention mechanisms. So the paper presents the transformer, as I've mentioned before, a state-of-the-art model architecture for sequence modeling and transduction problems such as language modeling and machine translation especially. The transformer replaces the recurrent nature of traditional approaches with an attention mechanism, following for more parallelization and improved training times. So the authors also demonstrate the efficacy of the transformer in the paper by achieving a new state-of-the-art in translation quality after just 12 hours of training on 8 GPUs. So now getting into the background part, the authors briefly review the encoder and decoder architecture of the transformer and its variants, including the convolutional sequence-to-sequence models, and highlight their limitations. So they also provide an overview of self-attention mechanisms and their applications in NLP as well. So to give a brief overview, the transformer differs from previous models such as, for example, an extended neural GPU, ByteNet, or as I mentioned before, convolutional sequence-to-sequence model, as it reduces the number of operations required to relate signals from input or output positions to a constant number, thus making it easier to learn dependencies as well. So the transformer is the first transduction model that uses self-attention only without relying on a sequence-aligned RNNs or convolution as well. So in the following sections, the authors also described the transformer in detail and explained the motivation behind the self-attention, and also compared its advantages over other previous models as well. So we'll discuss about the transformer architecture that is mentioned in the paper. So the parts of the transformer include encoder and decoder, as I mentioned. It works on the attention mechanism. Then we'll discuss about the types of attention that is provided in the paper. Then how the attention mechanism is applied to the transformer model. Then also we'll talk about the position-wise feed-forward networks, embeddings and softmax, and positional encoding in detail. So coming to the proposed architecture, the authors present the transformer architecture, which consists of a multi-head self-attention mechanisms and position-wise fully connected feed-forward networks. The architecture operates on a sequence of vectors, and the authors demonstrate how the self-attention mechanism can directly model the dependencies between all positions in the sequence. So to give an overview, the transformer architecture is a type of deep learning model, and it is used mostly for NLP tasks, such as text classification, language translation, and especially text generation. So the basic structure of a transformer model, as you can see in the figure provided, includes an encoder and a decoder, each consisting of multiple layers. So the encoder takes in the input sequence and produces a continuous representation of it. And the decoder then takes the encoder's output and generates the final output. So both the encoder and decoder each are composed of a stack of 6 identical layers. The encoder layer has 2 sublayers, the multi-head attention mechanism and a fully connected feed-forward network. And whereas the decoder layer has 3 sublayers, a multi-head self-attention mechanism, multi-head attention over the encoder stack, and a fully connected feed-forward network. So both the encoder and decoder use residual connections and layer normalization as well. And so the model uses outputs of dimension D model is equal to 512, which is mentioned in the paper. And the self-attention sublayer in the decoder stack is modified to prevent positions from attending to subsequent positions. That is, to simplify it, it includes a positional encoding that helps the model understand the order of the input sequence. This is important because the transformer model doesn't have an explicit mechanism for considering the order of the input, unlike recurrent neural networks. So before we get into types of attention, we'll briefly understand what attention is. So I need everyone's attention. An attention function can be described as mapping a query and a set of key value pairs to an output, where the query, keys and values, and as well as outputs are all vectors. And the output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. So here, the first diagram shows the scale dot product attention.
So Sujith, to put it in the context, where do the Q, K, and V query keys and value, where do they come from? So is this the data you stream, or you take? Just give us an example of how you generate this K, Q, and V.
Yeah. So actually, the 3 components, query Q, key K, and the value V, are the input values. Like whatever the input, for example, this in the paper they have used translation of languages from English to German and English to French. So the sentences and words are given as input, and they are transformed into query Q and the key value pairs, and then they are given provided to the attention mechanism.
But that's the question. If I give you an English word, how do you get Q, K, and V from it?
Okay, yeah. So I'll get into the details now.
Okay.
Yeah. Sorry, give me a second. Yeah. So the first image shows the scaled dot product attention, which contains 3 components, that is query Q, the key K, and the value V. So given a query, the attention mechanism computes the dot product of between the query and all keys in a sequence, which gives us a set of attention scores. And these attention scores are then used to weight the values, which are then combined to produce the attention output. So, sir, I'll get to the answer of your question in a bit.
Yeah, I'm just trying. I mean, I understand all the diagrams. I understand what the dot product is, and of course, but what's the main point of creating those 3 vectors, and how you create those 3 vectors?
What I deduce from the paper is that the attention mechanism takes input in the form of queries and keys of dimension dk and values of dimension dv, which they have mentioned, and they have given certain values for the dimensions as well, and they're only taking certain number of inputs for the model to train on. So what I deduce is that the sentences are transformed into Q, K, and V. That is the query and the key value pairs, so that the input and output are already there present, so that it can learn from the input as well as the output.
Well, I guess I'm missing something basic here. Okay, so there Vladimir is saying something. Maybe you can turn on your mic and answer question.
Yeah, if I remember correctly, the Q and V, they're just, so if you're translating between, say, German and English, you're querying for like a vector that represents an English sentence, and then the value you're looking for is the translated German equivalent. So, but these
exactly.
vectors, they're actually coming from an embedding layer or procedure, whatever your embedding
Sure,
procedure is.
some vector representation of a word, right?
Yeah.
Yeah.
Well, in this case, I think they extended even beyond just word. It's like a whole like string of sentence.
Doesn't matter, right?
So I think the one limitation of transformers is you have like a fixed vector length for your QV. So you need some sort of embedding space to like map arbitrary lengths into like fixed size vectors.
Sure. And so now the only thing is left K. What is K now? So Q and V are some vector representation of whatever it is that you're trying to translate, or what is the K then?
I think K is also some vector. I don't honestly remember what exactly it is.
Yeah.
Let me see.
So what I assume is that K is the matrix representation of the Q and V value pairs, so that it is
No.
inputted
All
into
three
the-
are vectors. All three are vectors, as far as I understand. And then you have to take a dot product of Q with K, and from that you will, yeah. So okay, it still remains a question. But go ahead. Let's assume there is some definition, suitable definition of K, which is probably the most important thing here. But okay.
Yeah. So coming to the scaled dot product attention specifically, the paper introduces scaled dot product attention as a specific type of attention mechanism for use in the transformer model. So this attention mechanism takes input in the form of queries and keys of dimensions, and the mechanism computes the dot products of the queries with all the keys, and divides each by the square root of dk and applies a softmax function to obtain weights on the values. So
Do
the
you
attention
understand why you
function,
divide it by dk, square root of dk? Do you understand why there is a division?
Actually, the dot product attention is faster and more space efficient. However, for large values of dk, the dot products can become very large, and which can cause problems for the softmax function. So to address this, the dot products are scaled by the square root of dk.
Do you understand why there is a square root of k, dk?
I'm not sure about that.
Yeah, so it must be have to do with if the dot product has k numbers in it and they are like plus or minus 1 of order 1, then in order to get the sum to be of order 1, you have to scale it by square root of dk, because it's like a random walk type of thing. That's I think why they rescale it by square root of dk.
Yeah. So yeah, now I'll get into multi-head attention, which is the mechanism that they have used for their transformer model. So it is just a modification to the self-attention mechanism that allows the model to jointly attend to different representations of the input. So instead of using a single set of parameters to project the queries, keys, and values, the multi-head attention linearly projects them heads times with different learned projections to reduce the dimensionality. So each projected version is then used to compute the attention function in parallel, resulting in dv dimensional output values. That is, to simplify it, in multi-head attention, the input Q, K, and V are projected heads times with different learned linear projections to DK, and DV dimensions respectively. Then the attention function is performed in parallel on each of these projected versions of Q, K, and V, resulting in head output values of the dimension DV. The output values from each head are concatenated and projected to produce the final value. In this paper, the authors have used 8 parallel attention layers, that is the value of h, or the number of heads they have taken as 8, and they have taken dk, dv, and d model as 64 to reduce the computational cost.
So basically, if you set h, small h to 1, then it's your previous attention, right, with only one projection.
So
Okay,
that's why
but,
it is
then the
just,
question arises how to find all those projections. Is it something that you train for, or
so
it is something that you just set ahead of time by guessing?
So what I've understood is that to reduce the computational cost, they have used certain number of H values. Then they have trained the model. Then they thought they've reduced to that H value of 8 has been like efficient enough for the transformer model to learn and provide results from.
Mhm.
So the applications of attention in the transformer model. So the transformer model uses multi-head attention, as I've already mentioned, and it uses multi-head attention in 3 different ways. That is encoder decoder attention, where the queries in these layers come from the previous decoder layer, while the memory keys and values come from the output of the encoder. So what I assume is that the K could be the memory or the storage of those input and output value pairs.
Okay.
Could that be it? Yeah, so the encoder decoder attention layer is where the queries in these layers come from the previous decoder layer. And this allows every position in the decoder to attend overall positions in the input sequence. And this mimics the typical encoder decoder architecture in sequence to sequence models. And whereas coming to the second type, encoder self-attention layers, that is, in these layers, all the keys, values, and queries come from the same place, which is the output of the previous layer within the encoder itself, where each position in the encoder can attend to all positions in the previous layer of the encoder. And when coming to the decoder self-attention layers, it is similar to the previous one, where each position in the decoder can attend to all positions in the decoder, up to and including that position as well. So yeah, it is similar to the encoder self-attention layer. So in all the 3 cases, multi-head attention is used to enable the model to jointly attend to information from different representation subspaces at different positions as well. So coming to the position-wise feed-forward networks, the transformer model has a fully connected feed-forward network, which is applied to each position separately and identically. The feed-forward network consists of 2 linear transformations with a ReLU activation in between. The parameters of linear transformations are different from layer to layer, and making it like 2 convolutions with kernel size 1. And the input and output dimensionality of the feed-forward network given in the paper are D model equals to 512, and the inner layer has dimensionality DFF is equal to 2048, which are the numericals they have taken in their paper. Here, the dimension refers to the number of elements in a particular vector or matrix, and the elements refer to as the scalar values that make up the vector or matrix. So the equation which I have presented here represents a position-wise feed-forward network in the transform architecture, where X is the input vector of dimension D model. And the feed-forward network applies 2 linear transformations to the vector, as I mentioned, with a ReLU activation function in between. So the first linear function, linear transformation, is represented by XW1 plus B1, where W1 is the weight matrix of the dimensions, and B1 is the bias vector of the dimension DFF. So the output of this transformation is then passed through the activation function, that is ReLU, as I've defined, and which sets all negative values to 0 and leaves positive values unchanged. And the second linear transformation is represented by max of 0, 0, xw1 plus b1 into w2 plus b2, where w2 is weight matrix of dimensions dff into d model, and b2 is a bias vector of dimension d model. So this transformation applies a weighted sum to the output of the ReLU function and produces a final output vector of dimension D model. So coming to the embeddings and softmax, the model also uses learned embeddings to convert input and output tokens into vectors of dimensions D model. A learned linear transformation and softmax function is used to convert the decoder output to predict next token probabilities, and the same weight matrix is shared between the two embedding layers and the pre-softmax linear transformation, and in the embedding layers the weights are multiplied by root D model. Then coming to the positional encoding, the transformer model doesn't have recurrence or convolutional layers, which means it needs to incorporate information about the position of tokens in the sequence. To achieve this, the positional encodings are added to the input embeddings at the bottoms of the encoder and decoder tasks. So the positional encodings have the same dimension as the embeddings and are either learned or fixed. So in this paper, the authors used sine and cosine functions of different frequencies to create the positional encodings. Here, POS is the position of the token in the sequence, and D model is the dimension of the model, and I is the dimension of the encoding. So the positional encodings are designed such that each dimension corresponds to a sinusoid with a different wavelength, and the wavelengths form a geometric progressions ranging from 2 pi to 10,000 minus 2 pi.
So do you understand why sine, why cosine?
Yeah, so they wanted.
Why not exponent or power law?
So they wanted to find the position of the particular input, because the transformer doesn't have special functions of finding the position of the input variable, which is present in recurrent neural network and convolution neural network. So they have introduced positional encoding for the transform model to learn from. So they've used sine and cosine functions to find the positions of the input variable.
I don't understand why it has to be sine or cosine. I mean, all this is not clear. Why it cannot be some other function?
I'm not sure about it, sir.
Right. Okay. So yeah, let's see if there is some more. We can get some more analytical understanding of what's happening. So I think I think the key question was, what are the keys?
Yeah.
If somebody knows what the keys are, I think this will clarify a lot.
Yeah, so the key, I looked it up. It's basically, you can think of it as the self-attention or just attention mechanism as a dictionary, like a fuzzy dictionary. And then depending on the type of attention that you want to have, so transformer has like 3 types of attention. You change what the key value query vectors are. So if you have like the cross attention layer attention, then I think the key and the value are actually the same vector. And then the key and the value, and the query is, the different vector, the translation. And if you change the attention layer to, say, global attention, that changes that again to something else. So let me see.
Well, okay. So
yeah, so in the global attention, it's just all of them are the same, because you don't actually have, so the cross attention layer is where you're trying to learn attention between the 2 different, basically your input and your output, where you're translating from and to. And then for just self-attention, you don't actually have the data for the output. So you're just learning attention on itself. So you're feeding the same data for the
string of data.
query.
String of data, right?
Well,
you have a
represented by
words,
a vector,
and you want to like put another word in front of it, right? That's what you're talking about. You want to complete the sentence, like self-completion.
Yeah, I think the way they do it is they have the full sentence. Yeah, I think the way they train is they have the full sentence, and then the output is also a full sentence. But then when you actually run the model, you can do it sequentially.
Right. No. But you can also use. So I think this is applied to large language model, like when you complete the sentence, autocomplete, right? So you start writing something and then continues the whatever text you wrote.
So could it be the positions of the words which are in sequence? Because you need a sequence for the sentence to be comprehensive.
No, I understand everything. We just need definitions, right? So what's missing here is a definition. Okay, so figure out, maybe go ahead, say something, educate us.
Oh, I just found this from a post that was made on Telegram by Vladimir. So it's basically like the key value pairs in a Python dictionary. So for example, if you look at the code I posted on the chat, you have a key and value pair, right? So the keys are the sort of information that the dictionary has, and the values is that piece of information. So for example, for the key color, then the value will be blue, and age, you could get 22, type, maybe you want to pick up something, and that's the sort of data you're feeding into the model.
All right, mathematics is missing it.
Yes.
Well, for now, this is all trivial. There are some just tensors that represent some things and some indices being contracted. We just have to write down what those tensors are and what those indices are, and then everything will become more clear. Perhaps there should be a paper that somebody wrote about the mathematics of autoencoders. Maybe we should, somebody should look it up. Okay, Sujith, this is it, right? So let's say for now it's a dark forest for all of us what autoencoder is. And it is a trivial thing because the only thing they do is dot product, right? So
yeah.
so it shouldn't be complicated. Okay, maybe next time somebody will volunteer to talk about autoencoders. Are there any other questions, comments? Right. All right, great. I'll see you.